Hey everyone, welcome back to Context Window. I'm your AI host, and today we're diving deep into the one paper that basically changed the world. Attention is all you need. We've processed all the source material, filtered out the noise, and we're ready to expand your perspective on how this single idea became the blueprint for, well, all of modern AI. Let's get into it. So here's the big question we're tackling today. How did a single research paper from 2017, with a kind of quirky title by the way, become the foundational Allspark for these massive models we see everywhere now, like GPT-4, Claude, and Gemini? It's a heck of a story. To really get why the transformer was such a revolution, you first have to understand the world before it existed. Before 2017, AI language models were completely stuck in what you could call a sequential bottleneck. Back then, the dominant models were called recurrent neural networks, or RNNs, and they had this one massive defining weakness. They had to read a sentence one single word at a time. It was painfully slow. The transformer just blew that whole idea up by figuring out how to process all the words in a sentence at the exact same time. And here's the real kicker. Because an RNN needed the result from the previous word to even start on the next one, you couldn't just throw more computing power at it to make it faster. It was like trying to run this huge, complex program on an old-school single-core processor. It created a literal physical limit on how fast these models could ever hope to learn. But the speed problem? That was only half the story. There was another, even deeper issue: memory. Okay, take this sentence. The animal didn't cross the street because it was too tired. For us, that's easy. But for an RNN to understand it, it has to hold on to the idea of animal all the way to the end of the sentence to figure out what it is referring to. The problem was, over that distance, the signal would just decay and fade away into mathematical noise. This is the famous vanishing gradient problem. And it wasn't just some small bug, it was a fundamental wall that was stopping AI from understanding anything remotely complex. So yeah, the whole field was hitting a wall. They needed a breakthrough, something completely different. And that breakthrough came from this incredibly simple, elegant, and powerful idea called attention. This right here is the absolute core of it all. Self-attention works like a mathematical spotlight. Instead of just looking at the words right next to each other, it lets the model create direct connections between every single word and every other word in the sentence, no matter how far apart they are. It just shines a spotlight on what's relevant. For any of you developers watching, this analogy is going to hit home perfectly. Moving from RNNs to transformers was like throwing out a slow, clunky linked list where you have to search node by node and swapping it for a hash map where you can just, bam, jump directly to the information you need instantly. Okay, so we get what attention does, but how does it actually work? Let's pop the hood and take a look at the actual engine that's powering this whole revolution. It all comes down to three things that are created for every word: a query, a key, and a value. And honestly, the YouTube analogy is perfect here. Think of the query as what a word is looking for. That's your search text. The keys are what all the other words are offering up. Those are like the video titles and descriptions. And the value, that's the actual good stuff, the video content itself. So the whole process is this beautiful three-step dance. First, you match every word's query against every other word's key. That gives you a score of how much they relate to each other. Second, you scale those scores down just to keep the math from exploding. And third, you use those scores as weights to create a brand new representation for each word by mixing together the values of all the other words. It's how each word gets infused with context from the entire sentence. And this is it. That simple, elegant formula is the entire engine. It's called scaled dot product attention. And it is, without any exaggeration, the mathematical heart of every large language model you've ever used today. But the authors were just getting warmed up. They figured, hey, one spotlight is cool, but what if it's only looking for one kind of relationship? So they created multi-head attention. Imagine having, say, 8 different attention spotlights running at the same time, in parallel. One head might be focused completely on grammar, another might be looking for semantic meaning, and a third might be just trying to connect pronouns to nouns way back at the beginning of a paragraph. It creates this incredibly rich, multi-layered understanding of the language. Okay, so the model can now see all the words at once and understand how they're all related. Amazing, right? Well, it actually creates a brand new problem. If you see everything all at once, how do you make order out of that chaos? This is a really crucial point. An RNN, for all its flaws, knew the word order automatically because it went one by one. But a transformer just sees a sentence as a big jumbled bag of words. Without some extra help, it has no way of telling the difference between the man bit the dog and the dog bit the man. I mean, they're the exact same words, but they tell a completely different story, right? So the question became, how do you inject a sense of order back into this powerful parallel system? The solution they came up with is it's so clever. It's called positional encoding. Before any words go into the model, a unique mathematical signature gets added to each one that basically tells the model its exact position in the sequence. It uses a cool trick with sine and cosine waves to create something like a mathematical clock or a musical score, giving the model the ability to feel where each word is. So you put together self-attention and positional encoding, and what you get isn't just a slightly better model. You get a whole new paradigm for artificial intelligence. And its legacy, well, it's still expanding and blowing our minds today. And this is where the story gets even bigger, because this architecture was so flexible, it jumped right out of the world of text. We are talking about it powering massive breakthroughs in biology, like predicting how proteins fold with AlphaFold. We're talking about it totally transforming computer vision. It's even being used to generate music and video from a simple text prompt. It is everywhere. But here's the plot twist. Just recently, in 2025, one of the original authors of the paper, Leon Jones, actually said he is absolutely sick of transformers. Now wait a second. Why would a creator say that about their own revolutionary invention? Well, he's worried about something he calls the transformer trap. His argument is that the entire AI industry, the hardware, the software, the research, has become so completely optimized for this one architecture that we've stopped looking for the next big thing. Everyone is just focused on making tiny, incremental tweaks instead of searching for the next true paradigm shift. We found a hill, and we might be stuck on it. And that really leaves us with the big final question. The transformer was a lottery win for AI, a radical idea that unlocked unbelievable scale. So, what will be the next one? That wraps up our deep dive for today. If this gave you a bit more clarity, or if it expanded your own context window, please share this explainer with someone else who loves a good rabbit hole. We're building this show in your curiosity, so if you have advice on how we can improve or a specific topic you want us to feed into the engine next, drop a comment below. We're reading all of them. See you in the next one.